Welcome back. In this video, we're going to talk about an example that gives intuition about the cosine formula for the dot product. Let's take a look at the example statement. We're going to consider two vectors, vector x in R2, which is given by 4, 4, and vector y, which is given by -2, 0. Using these two vectors, we're going to analyze the significance of the cosine formula representation of x dot y. We'll begin our example by just calculating x dot y. We'll use the component form of the dot product to calculate it to begin with. We know that x dot y would be 4, 4 by the definition of x, dotted with -2, 0. I'm going to skip the steps because I think we're now local professionals. 4.0. Oh, I guess I didn't really skip many steps there. Sorry. So this would be -8. Recall that from our previous work, this being negative, we would guess that this means that theta is going to be obtuse. We'll actually confirm this in just a bit. Before we do that, I wanted to quickly recall the two norms because we're going to need those in just a bit. So let's find the two norm of x, and we'll do this one in the classical way, which is to take the square root of 4 squared plus 4 squared, which is of course the square root of 16 plus 16, and then this goes down to the square root of 16 times 2, which is of course 4 square roots of 2. We will also find the two norm of y, and we'll refer back to these, so please mark these in your notes. We're going to need these when we do the cosine formula. Two norm of y, we'll actually do this by the dot product formula. In this case, we would have y dot y, which is -2, 0, dotted with -2, 0, which is of course 4 plus 0, and that is 4. The moment that we know that the two norm of y squared is 4, this means that the two norm is the square root of 4, which is 2. So we have these two statements, one of which comes from the Pythagorean base definition, the other one comes from algebraic properties. It really doesn't matter which you use because they produce the same result. This one's really useful if you want to just avoid having to deal with individual components and you want to suppress the information in a operation. All right, as promised, I wanted to show you what the interpretation of these are. So here we have the vector x. Here we have the vector y. We're assuming both of those have initial point at the origin because we were not told anything different. When we when we took the dot product between the two of these things, we got a -8, which we were claiming because the dot product was negative and because the dot product was a measurement of parallelity, these were anti-parallel or they were oppositely oriented. So we were hoping that this angle was obtuse. Here's the angle theta. Let me write all that down. We saw x dot y equal -8, which was less than 0, which implies x and y oriented in opposite oriented oppositely, I think, which implies theta obtuse, right? And we can see that graphically. Let's do it analytically. We also know x dot y was equal to the 2 norm of x times the 2 norm of y times the cosine of theta. And we just saw that this was -8. We knew that this was 4 square roots of 2. And then we know that the 2 norm of y was 2. This is from the work we did previously. And then this means that the cosine of theta is here. So now we have -8 equals 8 square roots of 2 cosine of theta. And then this results in a analysis that the cosine of theta is given by -8 divided by 8 square roots of 2, which could be simplified as -1 over square root of 2. And we can actually find exactly what theta is using the arc cosine, or the cosine inverse function, which has a very specific range and domain to make it an inverse. And this ends up to be, do you see it? 3 pi over 4, which is indeed an obtuse angle. So that's one way that you can find the theta using the cosine formula. Sadly, this is not, this is how to find an angle using this formula. But this doesn't really, in my opinion, build intuition. To build intuition, I'm going to make a suggestion. Rewrite the cosine formula from the form that we derived it in. This form of the cosine formula, written like this one is the one that comes directly from the proof. Written as results from the proof. But sometimes when we prove things, the way that we prove it is not necessarily the way that is most wise to think about it. The proof could be a nice algebraic trick, but doesn't really relate to intuition. My favorite form of this is actually to bring the 2 norms over to the other side, and then to write the cosine as the dot product of the unit vectors between the two of these. And in our case, if we were to actually do these for the specific example we're looking at, x was 4, 4. And then we're going to divide that by 4 square roots of 2. Notice this division is actually a scalar vector multiplication. We're just going to multiply the scalar 1 over 4 square roots of 2 by the vector 4, 4. And then here we had the vector -2, 0, and we were going to divide that by its norm 2. So now we've got cosine of theta equals 1 over square root of 2, 1 over square root of 2. And then we're going to dot that with -1, 0. And the reason that this is kind of useful, remember, this is the unit vector in direction of x. That's what this is. And then right here, this is the unit vector in the direction of y. And if we look at the geometry here, what we've done when we shift these unit vectors is we've taken our original diagram, so here's the x and the y. When we took the dot product as -8, factored into that dot product was the norms of each of these vectors. And so it was kind of skewing or stretching the relationship between these two, the geometric relationship. When we normalize, when we take the vector divided by its own length, we focus simply on the geometric relationship without reference to the length of each vector. And if you look, we can now replace this diagram with an equivalent version that depends only on unit vectors. So here what you see in this particular diagram, this is now the unit vector along the direction of x. Here we've got the unit vector along the direction of y. It is the exact same angle in between these by definition, because all we did is scale both of these things. And then the cosine of this angle, when we actually go to take this, we're actually going to get the same value. So this would be -1 over the square root of 2, just by doing that calculation out. And what you'll notice is that is the amount of the x vector in the direction of the y vector, which is really interesting. So I think that's a much better way intuitively to grasp what the cosine formula is saying. In the next video, we'll talk about the other important use of the dot product to create projections of one vector onto the other. Are you ready?